Excellent. Well, thank you so much for having me today. You did a really good job of introducing me, so I probably won't need to talk too much about my first two slides, which is really just discussing some of the things that I've done in my career, both commercially and also in the community, which is great because it means that I can spend much more time actually talking about the content for today, which is awesome news. So here's what we're going to talk about today. I'm going to do like a really short, hopefully not too drawn out introduction to JFR itself. I'm guessing that most people here already know what JFR is, but maybe there are some people who don't. And I think it's good just to take a few minutes to introduce it and my kind of perspective and my point of view on it. I'm also guessing that some people, hopefully most people, also know what New Relic is. But it's also worth just doing a little tiny bit on that. This is not a sales presentation, so I'm not selling anything, and so much so that I don't even need to have the safe harbor slide at the start of my deck. So that's how much not a sales presentation it is. And then after a few slides introducing New Relic and just the way that our products tend to work, I'm going to talk about JFR and the story that we have about JFR and how we use it at New Relic. And it's kind of an interesting story. It's something that I've been working on. The journey that I'm going to take you on in that section is really the history of one of my projects over the last 2 years. So it's kind of a personal view for sure, but it also reflects where the company's been heading. And then I guess we'll talk about the future and where we're going next. So without further ado, let's talk about JFR. So there's really 4 things I want to show here. Just a little tiny bit of history about and how we got here. JFR itself, and I keep writing Java Flight Recorder, and I was reminded the other day by my counterpart at Datadog, Marcus Hurt, who is the lead for Java Mission Control, that we must actually always remember that it's supposed to be JDK Flight Recorder and JDK Mission Control, because Oracle are touchy about trademarks, and I always forget, but so does everybody else. So when I write JFR and JMC, wherever I've written Java Flight Recorder by mistake, you must imagine in your mind that it actually really says JDK Flight Recorder, and I will be sure to correct the deck for next time. But it's actually kind of an interesting bit of backstory, because that J in JFR has meant different things. Sure, now that it's open source, it has to stand for JDK Flight Recorder. When it was a proprietary Oracle product, it stood for Java Flight Recorder. But once upon a time, it stood for something else. Because back in the dim and distant past, it actually stood for JRocket. JRocket Flight Recorder. And that's actually where it comes from. And this is kind of a story that a lot of people don't know, is that JRocket, JFR has actually been around for well over 10 years. It dates back to JRocket, which was acquired by Oracle over almost 13 years ago now. So the thing that I want you to understand is that JFR is a really mature product. It's just that it's been proprietary for almost all of its life. Yeah, it wasn't until 2018, so over 10 years after JFR was started, that it became a fully open source product. But it's had this long, history of becoming a mature and well supported and production grade software product, but it's just a proprietary one. Okay, so let's just talk about the history a little bit. So in 2008, Oracle acquired BEA and the initial version of the flight recorder technology. And then we skip ahead a few years, they also acquire Sun. And now they have 2 virtual machines. So what are they going to do with them? Well, they're going to merge them. And eventually, Oracle decided that what they would do is they would base the next version of the Oracle JDK on the hotspot VM. But they would merge in selected features into hotspot from JRocket. And one of the major things that came across was flight recorder and mission control. So even as far back as Java 7, if you were an Oracle customer, you paid for support, you could get a version of flight recorder and mission control. Oracle went through several iterations of trying to persuade people to part with money for JFR and JMC. and that didn't go so well. So to cut a very long story short, Java 11, when it came out in 2018, was now fully released as open source. JFR was included as part of the open source Java 11. And last year, to bring us up to almost 1 year ago, the release of Java 14 came out with a second new API for handling JFR events, which is actually a streaming API. We'll talk about that a bit later. The other big thing which happened last year was the backports. So the Java flight recorder technology, it's kind of a strange thing. It starts as proprietary. It's present in Java 7 as proprietary. It's present in Java 8 as proprietary. A slightly different version of it is open sourced as part of Java 11. And then that open sourced Java 11 version is backported to OpenJDK 8. So as of right now, you can actually get JFR in Java 8. Hopefully everybody's on Java 11 now. I hope people are. But for those people who are still stuck on Java 8, all is not lost. You can, if you upgrade to the latest versions of Java 8, you can actually get a version which has JFR capability as well. So that's kind of cool. So that's where we are. We have open source JFR in Java 11 and in latest 8, and also a new version with streaming capabilities in Java 14. Okay, so just to remind people what JFR does, there are two components. There's JFR, which is the profiling engine, which gathers diagnostics and profiling and telemetry information while a Java application is running. It is weaved deep inside the VM, and it basically touches every part of the operating and housekeeping of the virtual machine. So the sorts of data that it generates from within Java Flight Recorder is not necessarily anything which is attached to an individual thread. Some things are, as we'll see, but many other things are not. Things like garbage collection, things like JIT compilation, these things are not attached to any specific application thread. And yet they still generate telemetry data. The big surprise, the big win though, with JFR is the overhead. Oracle claim that you can do 1% of steady state performance. In practice at New Relic, we've observed that it's a bit more. There's a bit more to it than this. The JFR has what are called profiles, and a profile basically is a collection of events that you can either choose to collect or not. There are 130, slightly more than 130 different events that are possible to observe in a JFR event stream or a recording file. And the way that it works is that you can customize this completely, or you can just select one of two predefined profiles, and they have certain sets or subsets of the possible events switched on. As with everything in performance, there is a trade-off to be made. If you turn on absolutely everything, it has more runtime overhead. If you choose that you're only interested in a certain small subset of events, well, you don't have to pay the runtime tax for the other events because they're just not generated. And then the file will be read in, as we'll see, mission control. So how do we do this? What's the sort of simplest and most classic way of getting started with JFR? You pass a command line flag. So that's the easiest way to do it, is to just say, I'm going to start up my JVM, and it's going to have the command line flag to start a recording. This results in a high performance binary output file, either from one of the two standard profiles, which are called default and profile, probably the world's least imaginative names, and it's kind of makes them hard to talk about when you have to say to people, oh yes, well, you need to run your JFR in the profile. People look at you strangely when you say that. So why they couldn't have been given, I don't know, more sensible names like standard and profiling would even be better than profile, but never mind. The problem with this, of course, is that it's challenging to work with in containers. And that's something I'm going to come back to, because that was a major stumbling block for us making use of JFR at New Relic. We're very into containers, as I'm sure many of you are as well. And the lack of direct support for containers, or the difficulty of working with it, but was a problem. But never mind. Let's look at how you might start this up. So we have just this single flag that we're going to pass to the JVM at startup. It's a -XX flag, and it's got a whole bunch of options here. You can see that we're going to tell it to record to disk, and a maximum size. So how big a buffer of events would you like? Well, in this case, we're going to say a gig. And what this is going to do is this is actually going to produce a recording which is kind of ongoing. If you want one which is only of a fixed duration, you can use the second invocation that I've shown you here, which will begin recording at the start of the JVM, and it will record for 200 seconds and it will stop, which is fine if you have a short running program or something you want to do some performance analysis work on. But this is kind of a little bit inconvenient. If what we want and what we really wanted at New Relic was the ability to have a long running, continuous, real-time set of data collection without any defined beginning or end, without the need to stop and start it, just something that's going to continuously produce a stream of data effectively unendingly. So in the sort of the grand tradition of telemetry data, that's what we want it to look like. And as you can probably see, as it stands, this version of the JFR API just doesn't support that very well. There are some things you can do. You can use the J command to control it. You can start it and stop it, dump a snapshot, do all sorts of things from within J command. But those are all very manual tasks. There's no automation here. There's no sense of fitting this into just an always-on form of monitoring, which is really what we wanted. I mean, but you do what you can. We developed this way of using JFR effectively as a ring buffer, and where necessary, if there was an incident, we would SSH it into the machine and dump the buffer. And this allows us to do what I think of as going back in time. If you've configured a ring buffer of, say, I don't know, 3 or 4 hours worth of events, then whenever you log into the machine, you have the last 4 hours of history. So if you're an operations person and you get paged, well, providing you wake up quickly enough, you log into the machine, you SSH onto the box, you type the J command, and it gives you a dump of the last 4 hours. So you can go backwards before the incident happened and see the events and see the telemetry that led up to the problem occurring. This is not perfect. It's not great to have SSH running. It's fragile. If things break, you don't get the data. It's not very professionalized in a DevOps sense, but you can do it. And as an operational practice, it does give you access to these very, very high quality JFR recordings, which is what we want. Okay, so that was the first part of the thinking was that we had, and I'll explain how we implemented this exactly at New Relic when we get there. But what else can we say about JFR? What's in the data? Well, it ships with a command line tool, and the command line tool is called JFR. And this has a few things that it can do, but primarily it will print the contents of a recording file. This includes things like the events, and it provides some basic filtering, and you can see the types of events available. So you can see things like the CPU usage, garbage collection, memory allocation, and so forth. So let's actually do that. Rather than having nothing but slides, let's actually do this up here in the IDE. Oh, it's not the IDE, in the shell even. So let's JFR. Oh. Just make sure I'm running the right JDK. That will probably help, won't it? JFR print. And now let's just take one of these that I made earlier. Oh wow! I've just found a file which crashes the Java 11 JFR tool. That's cool. I can find a bug for that later. That wasn't supposed to happen. Never mind. Let me suggest instead what we're going to do is I'll just pick a few events, and maybe I'll pick a different file as well. But that's useful. So yeah. So okay. Here we go. Let's do this one. We're going to print the CPU load and the garbage collection, and I've got a file which I think is much more well behaved over here. So we're just going to print that, and it's just going to dump a load of stuff to screen like that. And sure enough, here are the two events that we can see. We can see garbage collection events, and they're produced in this form, which kind of looks a bit like JSON. It's not actually valid JSON, but it sort of is. It can show you what the contents of the events are. So the CPU load, for example, if you can see that one, if you look at the timestamps, you might be able to see that they look like they're about 1 second apart. And in fact, they are. But the garbage collection events, of course, occur whenever garbage collection occurs, which is not a regular cadence. As we know, garbage collection only runs when it has to run, when there's no more free space to be used. So the event stream is going to be a real mixture of different types of things. What other interesting things has it got? Well, let's run this one as well. And now hopefully we're going to see, oh, look, there's a whole bunch of different stuff here. Well, let's just stop that there. So we've got allocation data, object allocation in new TLab. Oh, that's handy. What type of thread was it? It was a thread called Kafka Consumer Auto Service. Yes, because here's a spoiler for later on. We do a lot of Kafka at New Relic. And so this is actually was, and look, you can see a stack trace that produced the allocation. There's a native method sample, so we can actually do method profiling. So there's all sorts of stuff in here, and this data is really, really cool. Anyway, so that's the command line tool. As we've just been talking about, there's some basic filtering. So you can reduce the amount of time and effort that's required to process in callbacks or in handling files. And you can filter things to say, should the event be recorded at all? What's the threshold? Do you want to handle stack traces? One of the things that you probably may know about Java is that handling stack traces is really expensive. That's why, for example, you must never create an exception object unless you're going to throw it. If you ever find yourself writing a temporary variable which is of type exception, that's almost certainly a code smell, because it implies that you may not be intending to throw it. And if you're not intending to throw it, you shouldn't create an exception. Okay, so there's a few other things you can do to reduce the overhead and provide some basic filtering. Next up is mission control. I included a bunch of slides about mission control with some screenshots on them because I was having trouble today actually getting mission control to run properly. And it turns out, and this is really quite amusing, that if you go to the Adopt Open JDK website, where mission control binaries are hosted, and you download them on Mac, you download a tarball, tar.pz, double click on it, and somehow the unzipping tool in Mac Finder breaks your download. It actually damages the binary if you try to open it. So that was just frustrating. I thought I was going mad. I downloaded the binary, unzipped it, and then it wouldn't run. So that was a very frustrating a few minutes earlier on. Okay, so this is mission control. This is the GUI tool for working either with live JVMs or with saved files. For those of you who have used the Eclipse IDE, you can probably tell that, sure enough, yes, this is in fact based on the Eclipse framework for building GUI apps. It feels very much like an instance of the Eclipse IDE. It can connect to live JVMs, but rather than do that, I'm actually going to use a file. But it does have a browser, which lets you see what's down the left-hand side. So let's open file. By the way, is there someone who hasn't fully muted? I hear occasional other blips on the line. So let's just find a file. Okay. So here we are. This is it's just parsing and walking through the file, and it's done. So let's see what we've got. How about let's look at some threads. Actually, let's start with the main application view. So this is like the heads-up screen. This gives you like a view of what's here. And this is actually just from a test application that I use. It's actually from Amazon. It's called Hypothesis, and it's a terrible Java programmer joke name, which provides an allocation benchmark. So basically, if you look here at this allocation level, you can see that it's basically providing very consistent allocation at the rate of about 0.5 GB per second. You can see a few other things that are present, and you can kind of turn these on and off here. You see, I can say, okay, I don't care about method profiling, I don't care about variables, or you can, if you don't mind having a slightly more crowded screen, you can actually have everything switched on there. If we come into the some of the other things we have here, we have memory, which now shows us things like a histogram. So up at the top here, you can see lurking. 87% of our allocation is in byte arrays. Okay, well, that's not surprising because this is just a test app, and mostly what it does is allocate byte arrays. You can also see that we have a bunch of other things in here, like the JDK internal object ASM annotation writer. Yeah, so that's one of the internal parts of the JDK, which is used in the creation and the handling of lambdas. Lock instances. Do we see any locks? Not really. Method profiling. You can see that this application is doing a whole lot of nothing. 86% of its time is spent in the Java util concurrent locks unpark method, which basically is the Java util concurrent equivalent of a synchronized block. So it's just sat there waiting. You know, the threads are basically idling while they're waiting for some condition to be met. You can go further on. You can dive into the allocation in more detail. Where again you can see that it's basically rock solid. That's what the application is supposed to do. So this GUI tool can tell you quite a lot. It can tell you about which GCs are in use, G1 new and G1 old. Great. Initial heap size of 256 meg and max heap size of 1 gig. We can also look at the pause times. So you can see the longest pause here. If I just mouse over it, you can see that the longest pause here is 3 milliseconds. So that's pretty cool. And then the sum of the pauses is the interface is a little tiny bit twitchy, 13 milliseconds. So over that period of time, which I think is about, what's that? Is that about 1 second? About 13 milliseconds of that was spent in GC. There's tons more here. I don't have time to do it all. So instead, I'm not going to. I'm just going to come back and move on. So yeah, so if you want to have a play with that, there's a separate download, jdk.java.net. And I will skip past all of my slides and come to the other demo that I wanted to show you, which is the API. So Java Flight Recorder is not just a file format, but it actually provides you with a way to handle the recording files programmatically. So hopefully people can see my screen now. I have a very, very simple program here. We just take a file name, we spin up one of these objects, a JFR file processor, and then we run it. And we take the file name that's been passed and turn it into a recording file, which is a new class. It's in the package jdk.jfr.consumer. And that's a new API with Java 11 and in later versions of 8 as well. And then we have this very stream-like way of processing it. I'm not sure why this isn't an auto-closable, but it's not. And instead that we just use a while loop and pull the events out of it one at a time. So one by one, we take an event, and all I'm doing with it is I'm going to call decoded, and that will return me either a map, or it's just going to return me a null. And if it's a null, we're not going to do anything. And otherwise, we're going to print out the resulting map that comes back from decode event. So I'm just stepping through the stream of events, and I'm processing the ones that I care about. So what does it mean by the ones that I care about? Okay, I have a variable called mappers, and for my mappers, for each one, I take the key and apply the test method to it against the event. So I test the event, and if it's true, and you're probably guessing what the key is going to be here, it's a predicate. So the predicate is used to test the event, and if it's true, I then use the value and apply it to transform the event into what I want to return out, which is a map of strings to strings. So that leads to this kind of interesting signature up here. I don't know if people can see this. So my mappers actually has this string. We have the map where the keys are predicates of recorded event, and the values are function of a recorded event to a map of strings to strings. So what that means is we end up with a map that looks a bit like this. So I'm building a map of a predicate, and I've got a helper method up here called testmaker, which takes in a string and returns a predicate which tests something. So in this, E is a recorded event. So I get the event's type, I get its name, and then I test it against the string that was used in this higher order function. So in this first example, the string I'm passing in is object allocation in UTLab. So what this is saying is that this mapper, this entry, is only interested in the event if it's the name of the event is object allocation in UTLab. And then down here, I've got a second entry, which is for garbage collection, which says, again, this entry is only interested in this event if it's a JDK.garbage collection event. And then the function is just expressed as a Lambda expression. And this looks a bit daunting, but it's actually really not. We take in the event and we transform it like this. We take the event and we return a map. And the map consists of the start time of the event, the end time of the event thread, the allocation size, and the TLAB. And I know all of those fields are on the event because I will only use this mapper if it's against the object allocation and TLAB event type. So I can basically, the fact that the events are not uniformly shaped, this is a way of getting around it. This is a way of saying I can use the name of the event to then understand what the shape of the event looks like and do the mapping accordingly. Because you can see that the two mappers do completely different things because the two different event types are very different shapes. So let me just run this. Gradle, of course, takes its time. Whenever a project needs to be run for a demo. Oh, Gradle, what are you doing? Well, I don't know why that isn't working. I tested that earlier and it worked fine. There we go. So if I just stop this 1 second. You can see some of the events that got outputted. So there's a whole lot of stuff from the Kafka consumer auto service. This is against the same file that I was just showing you in mission control. And you can see that there is lots of allocation information in here. And so somewhere there should be a GC. Yeah, here we go. So those are the sorts of fun things that you can do with the programmatic API for JFR. How am I doing for time? Well, I think I'd better move on. Okay. So that's the API demo. Let's meet New Relic. So there's really a couple of things I want to just talk about. There's a couple of slides just about New Relic. We're a performance monitoring company. We say we have the first observability platform, and we handle billions upon billions of events per day. I think we handle somewhere between 2 and 3 billion events per minute. So this is seriously high scale ingest of customers' events. We have a really cool website, which you're going to see later, which is called New Relic One, and it has this awesome programmable front end. So we have like React and GraphQL, and you can build your own front ends, you can build your own dashboards, and we've got this really nice query language, which we use as well. Java is the majority of our services, and Kafka is really, really important to us. So we have one of the biggest installations of Kafka anywhere in the world, and we also use a lot of Kotlin. So in one slide, What does New Relic look like? Well, there is an app, which might be a Java app. It could be something else as well. And in it, it has a New Relic agent, which is used to collect telemetry and monitoring and observability data from the application, whatever language it's written in. We have separate agents for separate languages: Java 1, .NET, Python, Ruby, PHP, C, Go, you name it, we've got an agent for it. And that agent is responsible for collecting data and sending it into our core data pipeline, which looks very much like this. You just have a big funnel, which basically ingests billions of events per minute, puts it into Kafka. There are a bunch of microservices. We have a cool high throughput database called NRDB, which is designed solely for observability data. It's a bespoke database designed exactly for the types of data that we handle. And then we take data from that and we put it into dashboards for you. So that's New Relic in one slide. So let's zoom in on the part where it says New Relic agent up there in the top left-hand corner. This obviously is a Java presentation. So what we care about are Java agents. And this is something which I'm not sure too many people are that familiar with. A Java agent is a tooling component that's written in Java, which uses an API called Java Lang Instrument, which modifies the bytecode of methods. As classes are loaded, an instrumentation API can modify the bytecode before they get loaded in. You install them using a startup flag. And the way that it works is, if this is the standard flow that we normally go through when we're class loading, you have a Java compiler, you produce a class file, the class file gets loaded, and it goes through the bytecode verifier. Well, before it gets verified, you can actually insert a transformation. So a Java agent is this blue box which is inserted into the class loader before the verifier runs. So that the bytes of so the byte stream which corresponds to the class file is intercepted, transformed, and providing it still passes verification, which it still has to do, it's then run in its modified form, not the version that was on the disk, which means that methods can have agent injected code before and after the main body of the method. So we can use this to collect timings and that kind of thing. There's a few details about how agents work. They need a manifest, they need a thing called a pre-main class and a pre-main method, which is a registration hook for the agent. So this method called pre-main runs on the main thread. So it has to return so that the main can actually run. So if you want to do anything which is long running, or you need a thread for what you're doing, which we do, you have to actually start up your own threads inside the pre-main method, because the thread that enters pre-main must exit so that main can run. There is a very simple hook for agents, and I'll probably actually just skip this and show you a real code example. Now, Java bytecode can be modified. There are specialized libraries used for this, the most well-known of which are probably ASM and ByteBuddy. Oh, and it's worth noting, I think we actually saw this earlier, that the ASM library is so widely used, there's actually a shaded version of it used inside the JDK itself. And ASM is used for things like Lambda expressions, and increasingly bytecode transformation and runtime bytecode generation is used even by the core libraries within the JDK. Okay, so let's now do a quick demo of an actual Java agent. Probably needed more than an hour for this, so I'm probably going quite quickly. So here we have an alloc agent. And just as I promised, there is a pre-main method. And the pre-main method says, create a new object called an alloc rewriter, and then add it to the instrumentation and then exit. So notice that you have to do it this way. If you want to actually to do anything else, I could, for example, do a thread.start in here. And the thread that I'm starting would survive the ending of the pre-main, and I could then use during the running of the main program. But never mind that. In this simple example, I'm just creating an alloc rewriter, which implements an interface called class transformer. Class transformer, it's got this slightly scary looking signature, the transform method. But the part I want you to focus on is that you get a class name, you get a class loader, should you need it. but you don't necessarily. And you get a byte array. So the byte array that's here is the bytes of the actual Java class that you're loading. So you can actually load, you receive the actual bytes as they have come off the disk, or wherever you got them from, and they appear in this this variable which I've called bytes. Notice also that the return value of this method is also a byte array. So a fancy, that could be a very fancy way of saying that what this method does is it transforms an array of bytes into an array of bytes. It takes the original byte stream and transforms it into the transformed one. The way ASM does this is you have a class reader which reads in the original bytes. You have a writer, which is ultimately what's going to, you can see this, it's going to be the thing which generates the output. And then you have a visitor which walks over the bytes as they're read in. So we've read in the bytes, we've got a standard untransformed version of the byte array, because what's happening is the class reader is parsing it into a metadata format which has all the fields and all the parts of the class, but the class has not been loaded. It's like a description of what the bytes mean in semantic terms for a class. And then we can create a visitor to transform that initial representation of the class into the one that we actually want it to, and then write it back out again. So the real meat of this example is actually this class here, which is called an allocation recording method visitor. Now, if you can't read bytecode, don't worry. The long and the short of it is what this thing does is if it sees a creation of an array, then what it does is it looks at what sort of array it is. If it's a primitive Boolean or byte, or is it short or char, or is it int or float, or long or double? Because the new array opcode will only get called for a primitive array. And having determined what type it is, it inserts a call to a static method called runtime cost counter record array allocation. Okay, so notice that when I run this, the new array opcode was what was there already. But before I call this opcode, I've inserted, and that's what this visit insum does, they insert additional bytecode operations into the stream. So effectively what's happening is it's like I'm rewriting the Java code to include a call to this method here. And the way that this works is it actually uses a thread local allocator, thread local long, to record how much allocation has been done. So that's an example of bytecode manipulation. It's an example of what we call weaving, to alter the bytecodes as they're loaded. And in this case, I'm just trying to make some sort of crude estimation as to how much memory that I'm actually allocating as my program runs. Okay, that was a bit of a deep dive into how a simple Java agent is written, a bit more than I'd expected. Never mind. So let's meet the new Relic Java agent. It's very large, very sophisticated, over 10 years in development, and it's used by many, many different types of user all over the world. It's quite possibly, it's the largest ASM code base that exists. Certainly, we've talked to some of the folks that maintain ASM, and I don't think they've heard of a larger or more complex use case than the one we have. We support Java 7 Plus, well, at least for the next few weeks. In a few weeks' time, we're going to be dropping support for Java 7, and will only be Java 8 and upwards. But the thing is that this is pure bytecode. It's all Java, so there's no native code here. So it runs on any platform that supports Java. Linux, Windows. I found out the other day it even supports the mainframe. So if you have an IBM Xeos machine somewhere, yes, our Java agent will work on it. Oh, And one of the big things, one of the other big projects that I've been working on since I've been at New Relic, it's open source. So all of the code, all of the experience that we have in manipulating bytecode and dealing with weird edge cases of class loaders is all out there in the public. We pivoted New Relic to being a fully open source company where every piece of code that touches a customer system is open source. And that was one of my big things from last year. I'm going to show you a quick diagram of how the internal architecture of the agent works. It's a little bit complicated, and it effectively has an internal microservice architecture which will be injected inside your classes. So your JVMs will actually have this internal service added into them, which has a bunch of different things that we can use it for. But the long and the short of it is that classes are transformed. You see weaved classes which send data into an API, and then we do some sampling, and the data is harvested, and we format it and send it over HTTPS to our edge collector. So that's what happens. The telemetry is all comes through this front door here and into the transactions and tracers before being sent up to New Relic. Wish I had more time to talk about it. There's loads of really interesting and cool things that happen there, but I've only got a few minutes. So what else? We at New Relic, we've been very interested in thinking about how we could converge this cool Java agent we have with JFR. And the way that we went through this is kind of where the story gets a little bit interesting. When I first joined, the internal landscape of Java was a bit of a mess. So one of the first things that I did was to persuade people that we needed to standardize on an open JDK distribution. And here's where being a vendor who customers send their data to is really interesting, because I was able to look at customers' data and see which open JDK distribution. You remember a couple of years back, Oracle changed the license, so you can't get free updates anymore. You only get 6 months of free updates, and then you have to upgrade the major version number. And people don't want to do that. I mean, Oracle says it's fine, but in practice, people don't do that. So we looked at our customer data, and what did we see? Lo and behold, the place that everybody was going to was adopt Open JDK. So it's a simple decision. If that's where your customers are going, then maybe that's the distribution that we should pick too. So we made that decision. We migrated all of our JVMs over to use adopt Open JDK and provided standard Docker images for internal use. And this is a project we call MOJIC, which stands for Modern Observable Java in Containers. It provides you, if you're an internal New Relic user, with a few things. You get a standard, up-to-date adopt Open JDK binary. You get SSH access. And critically, you get JFR support and standardized logging locations. So that our container fabric, which is basically our container product, which we use internally, it was set up in such a way that all applications could switch on JFR, and the JFR recordings would be available in a standard location. So this was kind of takes us up to, I guess, June or July of 2019. People were producing JFR, and they were analyzing those files using mission control. But in the back of my mind, I was still thinking, how do we combine this? How do we blend this with the Java agent? Well, and it turns out that the New Relic Java agent supports agent extensions. And what that is it's additional capabilities, additional functionality, or additional instrumentations. In some cases, some of our customers have even written their own extensions, which are their own proprietary things that they wanted, and just plugged into our API to take advantage of that. They place them in a separate jar, and then when the agent loads up, the New Relic agent, it dynamically loads any extensions it can find, and those capabilities start asynchronously, and they're added to the internal microservice architecture that we provide for. So that was an obvious way to do it, to do something with JFR as an agent extension. And then we came across JFR event streaming. Now, this is an API which turns up in Java 14, and it's not based on recordings. Instead of recordings and files, it lets you receive callbacks for JFR events, and you can respond to them immediately. So this then provides us with a data stream which the New Relic agent can use. We did do an initial release of this code based on JFR 14 event streaming. It's open source. the URL is in the slide. If you want to go and see how we did it, you can go and take a look. But if I show you in one slide how it works, once again, you can see that this is an agent main. It's an agent class. So we have the pre-main, which basically just starts up this thread. And then that's why this implements runnable, because we just pass a new instance of agent main into this and start the thread. Remember, because the pre-main method has to return. And then in this method, we spin up an event stream sender, and then we have this try with resources clause, which basically takes a new JFR recording stream and sets up a couple of events on it. So in this simple example, all it's going to do is it's going to take these events, the CPU load and the Java monitor enter, which is basically a synchronized block. So what this is going to do is it's going to give you a 1 second heartbeat on what the CPU load is, and it's going to give you an event every time a Java synchronized block, a monitor, is held for more than 10 milliseconds. And then having set up those two events on the stream, we just indicate that the sender object is going to receive callbacks for them. So this callback-based style is very, very easy, and everything's wonderful. There's just one problem. JFR streaming did not get backported. So that made me very sad. We produced this, we released it in time for Java 14, and then in the summer of 2020, it became, of 2019, which year was that? No, it was 2020. It became apparent that the streaming API was not going to get backported. So that made me sad, and I came up with pseudo streaming instead. How does this work? Well, it's a principle that I've used quite a few times, where what we try to do is we try to adapt to the API that we wish we had. Okay, so it's like a forward adaptation onto the streaming API, which is what we really wish we could have for Java 11 and Java 8. And the way to do that is to start a JFR recording over JMX, keep it running, a ring buffer of 20 seconds. And every 10 seconds, clone it and dump it. That gives you the last 20 seconds. But if you're taking that every 10 seconds, you're going to kind of get overlapping recordings. So you can convert each recording to a stream of objects, deduplicate it, and send the resulting stream up to New Relic. And that's what we do. I don't have time to demo the code for you, unfortunately. It is all up there on the New Relic GitHub repo. So you can go and look at it, and you can go and see how the code works. But I should move on to finish. So we have 3 deployment options today. You can deploy either as a standalone agent without the New Relic agent present for high performance. You can use a standalone process, which can also cooperate with the Java agent. And coming very soon, there'll be an agent extension to allow you to use this in the same way that the Java 14 version has been used. I was going to talk a little bit about observability and profiling, because the last piece I want to talk to you about is profilers. I would just say that there are these 3 classes of tools. I would always remember this quote from Donald Knuth. Part of the problem with profiling is identifying the code which needs to be looked at. In this case, I'm going to talk about execution profiling. And you should ask Kirk Pepperdine, if you get him, to tell you all about execution profiling and intrinsic time and how the profiling tools break down. So traditional profilers are things like JProfiler and YourKit, and they're fine, but they rely on sampling. Whereas things like Honest Profiler and Async and JFR do not rely upon thread sampling. So this leads us to a discussion of what I'd really like are some flame graphs. And everybody loves flame graphs. And hopefully, it's now time for the last one of my demos. Let's see if this works. Okay, so what we have here is actually the New Relic front page. You might notice, if you're eagle-eyed, that this is our staging site, and that's quite deliberate, because what I want to do is actually show you some data from an actual New Relic production system. And we actually are one of the largest users of our own system. So we actually have almost 2 million different things within the New Relic environment that we actually monitor using with New Relic. So there's kind of a problem that if you use your production system to monitor your production system, and your production system has a problem, where do you go to look at it? So for that reason, our production system is monitored by our staging system, and they're separate. So if our production system has an outage, it is actually still sending its telemetry data into a system that we can access. And that's how we do this. And here is one of my applications. It's called BMDS, Basic Metadata Services. And you remember I talked to you earlier about how we were able to see from our customer data that most of our customers who weren't using Oracle were using Adopt Open JDK. This is the system that generates and handles that data and writes it into our NRDB database for us. And there's a whole bunch of different things we can look at. The one I want to show you is real-time profiling for Java. Here is my cluster, and it's showing me the last 2 hours of my cluster. There are 4 different containers running here, and there's this heat map which basically shows you that one of these things is not very happy. See, it's using about 56% of CPU. See what the latest reading was, 56%. That one's running at 45, and I've got a feeling that the threshold for this, where it starts to warn on CPU, is 50%. Now, that 56 is kind of okay, and it seems to be pretty stable if we look at this. So I'm guessing that this one is probably just maybe suffering from a noisy neighbor. So let's actually click on it. Let's see what's happening live. And here we are. This is all of the JFR data that we're looking at here. You know, like we can see the CPU utilization. We can see the user and the system time here. We can see how the heap's doing. The heap is just kind of fluctuating. That's about 650 meg here, some heap used. That's fine. We can come down. You can see GC pauses. The longest GC pause we're seeing goes up as high as 40 milliseconds. And what I can tell is that this is really a pretty happy, looking JVM. There's not a lot here to really worry about. Up at the top, we've got that flame graph, which looks like a lot like the perf flame graphs that exist. And I can pick something like, let's see now. Let's pick this one. So you can see some of the internal code that we run here. We're looking at the agent lifecycle events, and you can see that we're using Kafka with Snappy and Thrift, and that's where we're spending a certain amount of time there. When I zoom back out, it's not a lot of time. Again, some of these things are actually just all about weighting and polling methods. So there's not a lot happening. It seems to be actually pretty healthy. But if things were going wrong, that would be the kind of data you could use to help diagnose it. If I come down, you can also see things like thread utilization and object allocation on a per thread basis. So if I pick these out, you can see probably there's the Kafka auto server, which is running at about 250 to 300 meg per second. But if I pick one of the others, you can see that they're down in the kilobytes range. The only one which comes anywhere close is a Kafka producer thread, which is doing about 8 meg per second. We've got network reads and network writes as well, and just a lot of good health check data for our VMs. Okay, so that was the demo. I think I'm pretty much at time. So let's talk about the future to wrap up with. The market is moving more and more towards open source instrumentation. And we think that a lot of people are going to be using open interfaces rather than weaving. There's a lot of emphasis on explicit event generation rather than the automatic transformation techniques. And technologies like OpenTelemetry are going to become more and more important. At New Relic, we absolutely support that. We can handle open source event sending right now today. All of our sending formats are themselves open source. So if you want to use our vendor format, which is open, you can do. If you want to use something else like OpenTelemetry or Zipkin or Spring Micrometer or anything like that, Prometheus, any of those technologies, we support all of those as well. And for JFR, the technology is open source now. It's backported to 8. It's a key part of the ecosystem, but it's not all of it. We see it as part of the pivot towards open instrumentation, and we're looking very closely about bridging to open tracing and open telemetry and other open source tools. So if you'd like to know more or do stuff to help, upgrade to 11, make some JFR recordings, experiment with mission control, try out JFR. If you want to, you can try it out in New Relic for free. We absolutely have a free tier where you can send us up to 100 gigabytes of traffic per month for free forever. So that's the story, and I guess that's the end. I have a couple of books if people are interested. There is a link at the bottom on the screen and a code for 40% off my new book, The Well-Grounded Java Developer. And the other thing that I should say is that I'm hiring. So if you've been excited by JFR and the other things that I've seen today, I'm hiring for a couple of different roles. Please reach out. I'd love to hear from people.
Thank you, Ben.